Alright, welcome back to this lecture on forces for Physics 2048C and 2053. So, what are exactly forces? So we talked about earlier vectors and kinematics, and now we're on to a section called kinetics, which is the study of forces on an object and no longer just the velocity, position, and acceleration associated with it. So, what exactly is a force? Based off of your knowledge of the world and how you perceive the world, you'll probably notice if you push something, it'll move. If you pull something, it will also move. And essentially, Newton, when he came about this, he found the exact same thing. And a force is quite literally just a push or a pull, in very simple terms. So anything that can cause some acceleration in the object, that is a push or a pull, that is a force. So, it can cause the object to change velocities, which means that it has some kind of acceleration. And when Newton started going about this, he derived some laws of motion that are still applicable, obviously, today. So, for instance, Newton's first law was that an object in motion stays in motion unless acted upon by an opposite or by a force, which is essentially if something is standing still, it will continue to stand still, or if it's going at some constant velocity, it will continue to stay at that constant velocity in a vacuum, unless some other force, something that can cause acceleration, is acting upon that thing to cause it to slow down or to speed up or something along that line. So, Newton, doing all this, came up with a second law, which is he derived, and we'll get to this in later lectures as to why this is the case, but he says that if there's some object and it has some number of forces, the sum of all the forces is going to be equal. This could be, 6 different forces. The sum of all the forces in their respective directions, so that includes the sums of the forces in the x and the y, because in our force, you see this little thing here says it's a vector, is equal to the mass times the acceleration in said direction. So you can obviously break this down into the sums of forces in the x direction is equal to ma is equal to max, and the sums of forces in the y direction is equal to may. Now, again, like we just said, what if there's multiple forces acting on this thing? Like take this little block here, for instance, and it has 2 fingers that are pushing on it from either side. What do? If there's not just one force, it can't just be the force is equal to mass times acceleration. You have to do something called a sum of forces equation and a free body diagram. So what's a free body diagram? A free body diagram is essentially we're going to be isolating the object, cutting it off from the rest of the world. So this is the object, we cut it off from the rest of the world, and we draw it at some point in space. So we isolate the object into a point, draw a coordinate axis system, draw forces on a dot, and write a sums of forces equation. So, looking at this thing, right, we cut this off from the rest of the world. There's no fingers touching it. It's just a box. We can draw the box as just a point in space, like this. It's just a point in space. And we draw the forces that are acting on the box. Well, there is a force going that way and a force going that way. So that's exactly what we have here. Force 2 and force 1 are both acting on this box. And we can define a coordinate axis system to make it easy to work with, so we can see what we're summing eventually. So right here you see we have sums of forces in the x direction, because these are both going in the x direction, is equal to force 1 minus force 2, because we said this is the positive x direction, right? So we choose whatever's going towards the positive direction, which is F1. And if it's going the opposite direction, we say it's minus F2, remember vectors, is equal to mass times the acceleration in the x direction. Now, let's say both of these forces were pointing in this direction, you would have F1 plus F2 is equal to mass times acceleration in the x direction. So again, back to vectors. This is just basic vector subtraction, vector addition. You're breaking up into components of the x and the y, and that's how you go here. So let's say we have a box now that's in 2 dimensions, like this. This is a box here which has forces acting on it in both the x and the y. You see there's a finger here, finger here, finger here, finger here. Well, what do? Same exact process. You draw a free body diagram, isolate it from the world. Draw a free body diagram as just a point. draw the forces that are acting on it. So this force is going up and through it, this force is going down, this is going to the left, this is going to the right. It's exactly what we have here. Make sure you always have a coordinate axis system so that when you write the sums of forces equation, you can write them accurately. If it's going towards the direction of the positive, it is positive in your sums of forces. It's going away from that direction, it's negative. So positive force, negative force. And you can write a sums of forces equation for this. So as you see here, force is a vector, write the sum of forces equation in the x and the y. So you see I wrote a sums of forces in the x and sums of forces in the y. We have F1, which is going to the right because it's positive. We said that here, F1. Minus F2, because F2 is going to the left, so therefore it's negative. And that's equal to m times the acceleration in the x direction. And sums of forces in the y, we have F4, which is positive because it's going up in that direction of the positive y. And then F3, which is going down because it's in the direction of the negative, is equal to MAY. So let's do a little practice. We have here a high-performance dragster, so some car. It has a mass and accelerates at some acceleration. It wants to know the force on the dragster. Well, we can draw our free body diagram. This is our dragster, just a dot again in space. And we'll draw a coordinate axis system here. So we have x and we have y. And we'll draw the forces on it. Well, there's only one force that's accelerating this dragster, one force that's causing this dragster to move, right? And that's the force of its thrust. It's the force that's acting on it. Now, what is that force? Well, we can say that the force in the x direction, right? Force is equal, there's only one force acting on it, so it's just going to be equal to mass times acceleration in the x direction. Well, we have the mass right here, and we have the acceleration, so this is literally it. That is our entire expression. We know that's just going to be max. That's our answer. Now, how do we solve for the final velocity? Well, we solve for an acceleration, right? Because we have the force, we have the mass, we have the acceleration, so we know the force. We can solve for the final velocity just using this acceleration, right? And plug into a kinematics equation. Nothing else to solve for there. So we can just do, we have the acceleration. Let's see which good kinematic equation we can use. We don't have time, so we just want one that doesn't have time with it. So likely this one here, which is vf squared, is equal to vi squared plus 2a delta x. So we'll write that one down. So here we go. So vf squared is equal to vi squared plus 2a delta x, or 2ax. Well, we know that there's some positive acceleration, so we have that. We know this x is going to be L. We're looking for the final velocity, but we know it starts from rest, so it's going to be Vf is equal to 2 times that acceleration times the length and the square root of that. And there's our final expression. Alright, let's try it now with a block. So this block is sitting on some frictionless surface, which means that there's no forces on the ground here that are holding it in place. Think about this is like ice. This is sitting on ice. It's very smooth. It can slide. There's nothing that would stop it from moving. Since it's on a frictionless surface and is subject to two forces acting on it, F1, F2, and theta, now it's asking for a free body diagram of this box. So let's do it. We can isolate this from the rest of the world. And once we do that, we draw it as a point. So we'll draw it as a point. And we'll draw our coordinate axis system. So we'll do y and we'll do x. Now we want to draw the forces on this. Well, we see this F force here is pointing in this direction. So this is F1. And we see that this F2 force is going at some angle below the horizontal in that direction, right? So I like to draw these dots so I can see exactly what I'm doing while I'm doing this here. We know that this is the angle, so we know that this is that angle, theta, right there. So this here is our free body diagram. Now, let's see, the total forces in the x direction. Well, we know, again, now we can break this up, right? We're talking about vectors, so we can break this up into this force in the y direction and in the x direction, and this force is only going in the x direction. But let's write our sums of forces equation. So we have sums of forces in the x, sums of forces in the y. Well, in the x, since we define positive x as going to the right, we have a negative F1. But we have this component right here going in the positive direction, right? Because it looks something like that. So we have plus, and that would be f2, yep, f2, and that, remember this is the cosine because it's adjacent to the angle, so it'd be f2 cosine of the angle theta, and this would be equal to whatever max is going on in there. And sums of forces in the y direction, which is what I asked for next, is going to be just the only, well, actually, we do have to add a few extra things to this free body diagram, which are needed. So if there is an object that's touching, so for the x direction, this is good. We have nothing else going in the x direction, and this works just fine. Now, these are the only applied forces to the object, but there are two other forces that are on this object because it's sitting on a surface, and that is called the normal force that's going to be added to it, and there's also a force of gravity on this object. So the normal force always points normal, which is perpendicular to a surface, any surface. So this is the surface here, so the force is always going to go straight out of that surface. If this box was on an angle like this, the normal force would be going at an angle. Gravity always points straight to the bottom of your page. So like this, in this case like this. So we have our normal force going that way, and we have our gravitational, or force of gravity, which we can just label as mass times gravity, right? Because we said it's ma. In this case, it would just be mg going the y direction. So, in the x direction, we're good. Let's write it for the y direction now. So, in the y direction, we have n going up, right, because this is positive. We have minus mg, because that's going negative. And we also have minus f2 sine theta, and this is going to be equal to may. And that's because this is going negative, right? It's pointing downwards, so that's minus f2, and this is opposite, so it's minus f2 sine theta. Now, it wants the acceleration in the x direction, so what we're going to do is we're going to use that equation that we wrote up here for the sums of forces in the x, just this little one right here, and we can solve for that acceleration in the a direction by just dividing out by mass, right? We divide both these by mass, and we have f2, I'm just going to move this over to this side to keep it a little nicer, is equal to ax. We divide all this by m. And there's your acceleration in the x direction. So that's how you solve a basic free body diagram equation. So we're going to talk about doing another one of these here. This is another practice problem that we can do. So we have this block, and it's sitting, it has two ropes that are attached to it. And these are called tension forces, two ropes that are attached to it. And they make an angle alpha and an angle beta with the horizontal. As you can see, this is that angle alpha, that's the angle beta. So it wants to draw the free body diagram. So we isolate this into a point, right? Here's our point. And once we draw that point, we're going to draw all the forces that are acting on this. We have a tension force pulling that way because it's holding it up. We have another tension force going that way, holding it up. We'll call this T1, this T2. Now we also have gravity. Don't forget gravity. If an object has mass, it has gravity. So we have the force of gravity acting down, but this is not touching a surface, so there's no normal force. Now what I want to do is add in those angles. So we have beta here. We have alpha here. And now we can draw a sums of forces equation for it once we define our axis. So I'm going to call that positive y, that positive x. Let's write our sums of forces equation. So sums of forces in the x, we have going in the positive T2 direction, right? We can break this up into its components. So like that and like that, like that and like that. So in the positive x direction, we have T2 cosine beta, right? Because this is the adjacent angle here. This is the adjacent side. So T2 cosine beta minus, because this is going backwards, right? Vectors. T1. Now, take a look at where the actual components are. This here is the y. This here is the x. So it'd be minus T1 sine alpha. Careful, because this is the opposite side from this angle, from the alpha angle. So it'd be minus T1 sine alpha. And that is equal to 0 because it's being just suspended, it's not moving. So it would be, you could write max if you'd like, max, but if it's not moving, we know it's not moving because the actual question says it, then this acceleration goes to 0, which means this whole side just equals 0. Now let's write the sums of forces in the y direction. So in the y direction, we have t2 sine beta, we have plus t1 cosine alpha, right? Because now this is the adjacent side that we're talking about, and these are both pointing positive, minus mg. This is also equal to 0 because it's not moving in any direction whatsoever. There's no acceleration going on to this. So what we're going to have here is we are looking for the tension forces, and we have two unknowns. These are the two unknowns, T2 and T1, and we have two equations. So this is perfectly solvable. So what I'm going to do T2 cosine beta is equal to T1 sine alpha, right? I'm just going to move this over to this side, and I'm going to solve for, I'll solve for T1 first, just so I can get, or actually, we'll solve for T2 first to make it a little easier on us later. So we'll do T2 is equal to sine alpha divided by cosine beta times T1, and now we can plug this T2 back into here. So we'll have sine alpha, so we'll have T2 sine alpha over cosine beta times sine beta plus T1 cosine alpha minus mg is equal to 0. Well, look at this, sine beta and cosine beta. If you have a sine divided by a cosine, that's a tangent. So we have T2 sine alpha tan beta plus T1 cosine alpha minus mg is equal to 0. So now we have, sorry, that would be T1. This should be a T1 in here. T1, there we go. T1. T1. Alright, T1 sine alpha tan beta plus T1 cosine alpha minus mg. So what we can do is we can move the mg over, and we have T1 sine alpha tan beta plus T1 cosine alpha is equal to mg. We can pull the T1 out, we can factor it out, and we have T1 sine alpha tan beta plus cosine alpha is equal to mg. And what else could we do here? We could probably just move it over, and that would give us our expression for our T1. So now once we have this T1, we can just end up plugging this right back into the first equation, right up here into our T1 spot, and solve for T2. So in part 2, we'll be talking about a few extra forces, including the frictional force and spring forces. So go ahead and watch that next. Thank you.